x squared over 2, then we can recast this equation in a way that looks like conservation of energy. In other words, the a dot squared term becomes v squared over 2, which represents, in a sense, kinetic energy. And here you have the potential energy term, and so the sum of kinetic and potential energy together equals a constant, which is controlled, the value of which constant is controlled by this quantity k. Remember, x is the moving coordinate, so x is constant too. And so really, we can see that this expanding sphere model of the universe has an interesting property we can understand in terms of kinetic, in terms of the total energy of the sphere as given by the sum of kinetic energy and potential energy. So, in particular, with analogy with typical Newtonian gravity, k, the constant on the right-hand side, is negative. Then you see from the top equation here, if k is negative, because rho is positive and a is positive, then the right-hand side of the equation is positive, and therefore a dot squared is always positive, and the universe expands forever. If k is negative, then dA by dt goes to, if k is 0, then dA by dt goes to 0 or t to infinity, and so the universe expands forever, but slows down, asymptotically stopping the expansion. And if k is positive, there is a point in the history of the universe where a dot becomes 0, and then it turns around. It happens for a value of a max, given by this expression. And so, in that case, what happens is that the universe stops expanding and then turns around and it contracts back to a big crunch. So you can see that depending on this value of the constant k, the entire history of the universe really hangs in the balance. And so we will make the connection with the cosmological parameters next. So we can see that k equals 0, the value of k equals 0 separates models that expand forever from recollapsing model. So k equals 0 is obviously an important point. It's an important place in the value of the parameters describing this model. So if we set k equals 0, with this equation here on the right hand side, I put k equals 0 in the top equation, and then I get an equality between a dot squared and an expression involving rho and a. It looks like this here. You see a dot over a squared is equal to 8 pi g over 3 times rho, and if we evaluate it today, so in other words, this is valid for all times, this is that's valid as a function of t. In particular, it is valid today, and if I evaluate it at the time today, is 0, and I define a, let me define that actually, a dot over a today, we define it as h naught, which is what we call the Hubble constant. Then we see that h naught is equal to 8 pi g over 3 times rho critical, which is the so-called critical density, which is rho today, such that the universe as k equals 0, it's a flat universe. So rho critical is defined, if you like this. So if you turn it around, if we define the critical energy density in terms of h naught, critical energy density is the one that separates an expanding universe from a contracting one, and at least if we neglect the cosmological constant, and it's given by this expression here, where h naught is the value of the Hubble expansion rate to the a dot over a. Because we don't know what the expansion rate is, we usually parameterize it in terms of a quantity that needs to be measured. So usually what we do, we write h naught equals 100 times h kilometers the second per megaparsec. And so small h parameterizes our ignorance of the current Hubble expansion rate. Small h is a dimensionless quantity of order 1. Typically, small h is measured to be 0.7 today. And so this is what appears here. You can see there is a small h in here, and then you can plug in numbers, and the critical density is 1.8 times 10 to the minus 29 gram per centimeter cube times h squared, whatever h squared is, but h squared is typically of order 0.5 maybe. So it's an extremely small energy density, matter density, 10 to the minus 29 gram per centimeter cube. So really, we're talking about very small densities, but because the universe is so big, the cumulative mass within any sphere is very large. Okay, so all of this is useful because it allows us to define cosmological parameters, which are the quantities that we are interested in measuring. In particular, define the density parameters, so-called density parameter omega 0, as the ratio between rho 0, that's the energy density today, divided by the critical energy density. That's the energy density that you would take to have a flat universe, k equals 0. And so, again, the omegas are dimensionless quantities, because those are densities divided by densities, and are essentially fractional densities. They tell you how much of the energy density of the universe today is expressed in terms of the critical energy density. So this is all very well, Newtonian. In fact, you can derive something very similar using the full GR approach, which we are not going to do. And if you do it in GR, you get the equation here, which is slightly different from the one that we had before. It's similar. It's got one extra term here. This term here, lambda over 3, which we didn't have, is the so-called cosmological constant term, where lambda is a constant with units of an energy density. Lambda is the only constant you can add to general relativity equations describing the expanding isotropic universe, subject to the constraint that you don't want to have higher than second order derivatives in your equations, and a couple of other constraints. In other words, lambda, this constant term, is the only modifications you can have from the standard field equations if you want to make them even more general. And that is the term that Einstein introduced in 1917, I believe, to make the universe static. In other words, lambda represents a repulsive force, as we shall see below, which can make the universe static but unstable. So you can have gravity, which makes the universe slow down, but you can have the cosmological constant lambda that makes the universe accelerate out. And if the cosmological constant is chosen just right, you get an unstable balance between the two. You have a static model of the universe, which is what Einstein wanted for Hubble discovered the expansion of the universe. So usually this equation is, so that's the equation for the expansion rate, and the equation for the acceleration, for the change in the expansion rate, is given by this expression here, where you can see again that the acceleration of the K factor A double dot is solely controlled by contents of the universe. That's to say, the energy density and the pressure of the fluid. P is the pressure of the fluid that is contained in the universe. And then there is also the cosmological constant term here, is lambda is non-zero. Now, P is the pressure of the fluid, which is usually parameterized in terms of the ratio to P of P to rho, or W, the equation of state parameter. And the equation of state parameter is 1/3 for radiation. If you have a constant radiation pressure is 1/3, is equal 1/3. 0 for matter, -1 for lambda. And this is a very exotic equation of state that accounts for the strange properties of the cosmological constant. It means that the pressure is negative, and that leads to an accelerated expansion, as you can see from the above equation. If To forget for a second this term here, let's forget this term here for a second, and let's say that we have rho, which is given by lambda, and p, which is also given by lambda. So the entire universe is made by a cosmological constant, and so p, if the universe is a cosmological constant, p is equal minus 1 times rho, minus 1 times rho. And so you can see that the term here on the right-hand side becomes rho minus 3 rho, forgetting c now. Sorry, it should be a minus, right? So if I take minus 1 here, let me do this calculation quickly. So if I take minus 1 for a cosmological constant, then we have that this term here is rho minus 3 rho, which gives us minus 2 rho. And so you can see that minus 2 rho, with a minus in front, it follows that A double dot is positive. And so if A double dot is positive, it means that the universe is accelerating with time, the expansion is accelerating. And so that is what the cosmological constant term does to the universe. It makes the universe accelerate. Instead, if you have radiation or matter, you can immediately see that the right-hand side term is going to be negative because there's minus here, and A double dot is negative, which means that the universe slows down. Okay, so that's the key difference. Cosmological constant makes the universe expansion accelerate, while other kinds of matter energy, such as radiation and normal matter, including dark matter, make the universe slow down. Fine, so now we can also look at the law of thermodynamics, which implies the following. Under the expanding universe, the matter density of the density of matter scales as the inverse cube of the scale factor. That's because of the conservation of mass. Number of particles is conserved, and the volume grows as a cubed, so density goes down as 1 over a cubed. If you have radiation, then it goes down as a to the 4th. And the reason is that you got expansion of the universe, in case the number of photons is conserved, so that's 1 over a cubed. But then the photons also get stretched and redshifted. They use energy as 1 over a. That accounts for an extra factor of a. And so their energy density goes down as a to the minus 4. But if you have a cosmological constant, because of the strange equation of state, the density in the cosmological constant is actually constant with time, which leads to this picture of the thermal history of the universe. So what happens is that as a function of the scale factor, so the scale factor grows in this direction, so time also grows from here to the right. So in the early universe, radiation was dominating, and radiation is redshifted away as a to the minus 4. And so the radiation density drops as a to the minus 4. And so the omega radiation, which is the ratio of radiation to the critical density, drops through the floor. At the same time, the matter density increases as a to the cube, and so omega matter takes over at a certain point in the history of the universe. When the radiation redshifts away, matter takes over. So omega matter becomes dominant in matter epoch. It's an epoch which happens about at the redshift of about 3000 or so. Before 3000, radiation dominates. After 3000, matter dominates. But then matter also redshifts away as a cube, and eventually the cosmological constant dominates because it's constant. And so when the matter redshifts away, there's a transition from matter domination to cosmological constant domination, and this crossover point happens at redshift of about 0.7. And nowadays we find ourselves in a universe that's almost cosmological constant dominated. We are about here. Actually, here, that's one. So we are in a universe that's almost cosmological constant dominated, and more and more cosmological constant dominated in the future. So that's actually one of the interesting questions of cosmology. Why do we believe the universe that's about two-thirds cosmological constant and only one-third matter? Because you can see this is a kind of a fine-tuned time in the history of the universe. A few billion years ago, we only had matter domination. In a few billion years in the future, we'll only have cosmological constant domination, but we are exactly in the transition regime. That's an interesting question and might have a statistical anthropic solution, which we don't have time to go into. It's an interesting question. So this is another view of what I just said. If you plot the evolution of radiation of the density parameter as a function of log A, so not log scale to make it more visible. So you see the radiation rho drops as a to the minus 4. So steep slope here, and then it becomes, there's a quality time when radiation and matter density are equal. Then matter becomes dominant, and that's the matter epoch, and it goes away there cubed, and then the cosmological constant takes over. So that's a curvature. If there's a curvature, it takes over, but in our case, we don't have curvature in the universe, and so this bit here you can neglect. Now the cosmological constant, the lambda domination, it's constant, and so this is the time in this universe where the lambda part dominates. As you can see, the universe goes through radiation-dominated epoch, matter-dominated epoch, and now cosmological constant-dominated epoch. Okay. Questions? So those omegas that I showed you are the cosmological parameters in each one of the components. So omega x is the density in x component today divided by the critical density, which is the one that's needed to make the universe flat. So again, those are dimensionless constants, and measuring them is one of the main goals of cosmology, because we can measure omega matter, omega lambda, and omega curvature. If there is a curvature to the universe, then we've measured some of the main properties of the cosmological model, and we know what the universe expansion looks like and what we do in the future. Now, because of the definition here, because the omega x's are defined with respect to the critical energy density, it turns out that the omega naught minus 1, so the critical energy density today minus 1 is equal to minus omega curvature, where omega curvature is defined as the curvature scale, kappa, divided by the Hubble parameter squared today. So we can associate energy density to the curvature of space, if there is one, and we call it omega kappa, while omega naught contains all of the other components, omega matter, omega radiation, and omega lambda. And those are the values that we want to know. Omega matter, as I told you before, is about 0.3 today, omega lambda is about 0.7, and omega radiation, because it has been redshifted away as inverse A to the fourth power, is negligible today, is over than 10 to the minus 5, so we can forget it in the mix today. So really, the only quantity we need to measure today are omega matter and omega lambda, and H naught, if we want to know what is the expansion of the universe. So kappa is this integration constant that we saw before. It turns out that you can, this quantity here has got dimensions of 1 over length square in general relativity, and so it's really 1 over square root of kappa is the curvature radius of the spatial sections of the universe. So tree space, there are only 3 possibilities for space in an isotropic and homogeneous universe. One is that kappa is equal to 0, so the universe is flat, Euclidean. Kappa is bigger than 0, the universe is closed, like a sphere, and the curvature parameter is less than 0. And kappa minus smaller than 0, the universe is open, like a hyperbolic space. Omega kappa is bigger than 0. And so with these definitions, finally, we cast the Hubble equation, Hubble expansion equation, like this, where we have the Hubble rate squared as a function of time is given by the Hubble rate today squared times the cosmological parameters, and each one of them evolves as a function of the scale factor according to the rules we saw before: radiation, matter, curvature, and lambda. And so really, if we can measure omega matter, omega curvature, and omega lambda, then we find out about the expansion of the universe. Okay, so that's a program of cosmology. Omega radiation is measured to this number here, as I told you before, because we have measured the amount of photons in the universe. Most of them are in the microwave background. We know the temperature of the microwave background, hence we know the energy density, hence we know the radiation. There are also neutrinos, which we treat to be massless, and if we assume there are 3 species of neutrinos, we know how many there are. So we can work out omega radiation from first principles, basically, and the measurements of the temperature of the CMB. So that's why we know omega radiation today. As I said before, it's negligible. But we need to find ways, observational ways, of measuring the other cosmological parameters. And so that's my next topic. How do we actually measure parameters in cosmology, and what are the relevant observables that will allow us to connect observations that we can make with this theoretical model of the universe? Questions? So this is the subject of cosmography. How do we measure the cosmological parameters? So, what are the observable? Let's start from the observer's point of view. First, we can observe redshift. Redshift define the difference between the observed wavelength minus the wavelength lambda 0 at emission divided by lambda 0. And we can observe it by taking spectra of objects, of course. And we can also write this down in differential form. So Z is equal to d lambda over lambda, which is equal to v over c, where v is the recession velocity of the object. So let's now try to connect redshift with the scale factor. So if we take we take our Newtonian model of the universe, and we ask what is the travel time dt that it takes for light to travel a distance dr, dt is equal to dr over c. And we can recast this as dA over h times a. So this r, we can recast dr as a over a dot times a. So we can just recast it like that. And now let's look at what happens to the wavelength. So d lambda over lambda is equal to d over c, but we also know that v is connected to h via this expression here. That's the Hubble law. So dv is equal to hdr. So we can replace dv by hdr. And now we can rewrite this as multiply and divide by the appropriate number here. So it's just using the equation above, this expression here. We plug that in, and we get finally the expression that d lambda over lambda is equal to dA over a. So in other words, lambda as a function of a is equal to a times lambda at the time of observation if we take a naught, that's to say a to the a to the 1. And so finally, if we just divide through by lambda, we get that lambda observed over lambda emission is equal to a minus 1, which is nothing but 1 plus z by the definition of z. And so we find that 1 plus z is equal to 1 over a. And so we find that if we measure 1 plus z, if we measure redshift, we've measured the value of a, the value of the scale factor at the time of emission. So in other words, measuring the scale factor is it's just the value of z, basically. And so by measuring redshift, we measure the value of the scale factor at the time of emission. Then A of t, as we saw before, depends itself on the cosmological parameters. And so the question is, how do we connect the cosmological parameters to the value of A? So to see that A depends on the cosmological parameters, consider this simple example, the so-called Einstein-de Sitter model. So Einstein-de Sitter model is a universe where you have no cosmological constant, omega lambda is equal to 0, and the curvature is also equal to 0. So you've got only matter in the universe, and that amount of matter is the same amount that you need to make things flat. The critical universe, omega matter equal omega 0 equal 1. And so if you go back, our expression here that we had for A dot as a function of the cosmological parameters, in the Einstein-de Sitter model, we have omega radiation we can neglect, curvature is 0, omega lambda is 0, and omega matter is equal to 1. So we get a very simple equation for A dot that we can integrate. So this is the equation down here. That's the equation with the simplification I just mentioned. So it's h dot over a squared is h naught squared times omega matter, which is 1, divided by 2 cubed. So we can integrate this equation easily, and we find a solution that a of t is given by this expression here. So in this case, we have the expansion, the scale factor connected to time through the value of h naught only, because we have omega matter equal 1, and so we know the cosmological parameter that the connection between scale factor and time still depends on one of the cosmological parameters, namely on h naught. So we can measure A, but we can via Z, but we cannot measure T. So the connection is precisely the one that we establish. And so that's where the definition of distances comes from, and that's the main observational instrument that we have in cosmology. So when we talk about distances, there are two main definitions of distances in cosmology, which is a little bit confusing sometimes because we think that the question of how far away is a galaxy from us should have a unique, unambiguous answer. But in general relativity, it turns out that you have to have a more precise definition of what you mean by distance, a definition that's based on an observable. And there are two ways of measuring distances. One is so-called angular diameter distance, where you consider a source of radius r on the sky, and you observe it to cover a solid angle omega, an apparent angle omega on the sky. And then you define the angular diameter distance dA here as the ratio, as the square root of the ratio of the area of the figure on the sky divided by the subtended solid angle. So just it's the ratio of the area to the apparent solid angle on the sky with the square root of it. So that's to say, if you have an object with known size and you can measure its apparent size on the sky, then you can measure the angular diameter distance to it because of the definition of angular diameter distance. Or we can define the luminosity distance. In this case, we consider a source of luminosity L, known luminosity L, and an observed flux F. And that defines the luminosity distance here is the ratio of the luminosity divided by 4 pi, S, but it should be S. This is the flux that we want. Just the luminosity divided by 4 pi, the flux, square root of it. And that's again, this is in analogy to the expression that you would have in the Euclidean universe. Of course, that's the distance squared is just the ratio of luminosity to flux. But so that's true in the Euclidean universe, but in an expanding general relativity universe, the two distances do not agree. They only agree for small redshift, in which case the angular diameter distance and luminosity distance are the same, but in general, they depend on the cosmological parameters and are in general different. And let me show you a couple of plots that show you what they look like. Here you can see two plots of the angular diameter distance normalized in an appropriate way as a function of redshift. And this expression depends on the cosmological parameters. So solid is the cosmological parameters that correspond to our universe, roughly, omega matter 0.3, omega lambda 0.7. You can see that the angular diameter distance as a function of redshift grows until redshift about 1 something, and then it turns around and drops, which is very counterintuitive. It means that objects on the sky, which have a standard ruler on the sky, an object of fixed physical size, and you put it at a different redshift, the apparent size on the sky of that object will decrease with distance, with redshift, I should say, as you expect, until a certain point, and then past that certain point, its apparent size will become bigger again, which is very counterintuitive. But you can imagine the same thing happening actually on the curved surface of the Earth. If you put yourself at the South Pole, and then you take a standard ruler and you start moving it towards the North Pole, and you look at the apparent size that it has to you on the South Pole, the size of the object will become smaller and smaller as it travels to the equator. But then when it goes past the equator in the North Cap, it will become larger again because of the way the light rays travel on the surface of the Earth. If you had a light ray traveling on the surface of the Earth. So it's a similar phenomenon that you get here. The apparent size of the object for this particular cosmology becomes larger again as a function of redshift. But you can see that if I change the cosmological parameters, so for example, if I make the universe flat but with no cosmological constant, the angular diameter distance is different. It's got a similar functional behavior, but the value is different. So objects at redshift of 1, for example, would look much bigger in a universe with no cosmological constant than they would in a universe with a cosmological constant by a factor of about 30% or so. And if I make the universe without a cosmological constant but with less matter in an open universe, which is the dashed line, again, you get a different behavior and one that does not turn around with distance. And so this is what the angular diameter distance does. The luminosity distance has got a different behavior. It does not turn around. So objects further away in redshift appear monotonically dimmer with redshift. But how deep they appear depends again on the cosmological parameters. So if you look at redshift of 2, for example, in the universe that we live in, which is a solid line, you see the luminosity distance is smaller than the luminosity distance is larger than in the universe here where you got no cosmological constant. And that means that in the universe with omega lambda, objects at a fixed redshift appear dimmer than they would appear in a universe with no cosmological constant, which is what we observe with the supernovae, as we shall see. So the point being that because of this dependency of the luminosity and angular diameter distance on the cosmological parameters, if we can find standard rulers in the sky and standard candles in the sky at different redshift and measure the angular diameter distance to them and the luminosity distance to them, then we can infer, using statistical methods, the value of the cosmological parameters. And that's the name of the game in cosmology. Measuring the redshift, measuring the angular diameter distance or the luminosity distance, and therefore use that measurement to work out the cosmological parameters that control those quantities. There is a relationship between these two. This relationship between the two distances, as I said, they are not the same, but they are related by these expressions. So you can express the angular diameter distance as the luminosity distance over 1 plus the redshift squared, actually. So the two do not agree numerically. They are not the same in measurement, but they are related to each other. Okay, so here's the name of the game, and that's what we want to do next. We want to do observational cosmology. We want to measure standard rulers or standard candles in the sky as a function of redshift. That gives us measurements of luminosity and angular diameter distance, and we want to use those in a statistical sense to infer the value of cosmological parameters. So as standard rulers, we're going to use the cosmological background and the barometric oscillations. As standard candles, the supernovae type 1a. Right, so that's what I want to say for this. Questions? Okay, so that's my sort of crash course in cosmology, just an introduction of what we need to do. And now, to look a little bit at the cosmic background, and we have to look at a quick introduction again to the physics of the CMB before we can talk about the statistical methods. Otherwise, it would be completely a black box. And again, this cosmic background could be a subject of a series of lectures in and for it. We can really talk about the details of the physics and the statistics of the microwave background for weeks and weeks. But we don't have the time to do that. So I've tried to condense in a few points the most important things that will hopefully allow you to follow a bit what these measurements are about. And I apologize for brevity, I apologize for lack of completeness and lack of rigor. There's simply no way we can do any of this in a short amount of time with any accuracy in the detail. So I'll try to keep it simple, but keep it anchored in basic physics that hopefully you remember from your undergraduate years if you haven't seen it before. Okay, Let me start with an introduction to the physics of the CMB. So as I mentioned before, the origins of the microwave background is at what we call the epoch of recombination. Now the name, if you haven't heard it before, the name is a little bit misleading because we call it recombination. That's the time where the universe became neutral for the first time. Although it's called recombination, that's the time where hydrogen recombined for the first time. So before then, the universe was too hot for protons to capture electrons and stay neutral. You had a bath of high-energy protons going around, and that meant that every time protons captured free electrons, a photon would immediately reionize that atom. And so what happens is that a plasma, essentially, for the universe, and that plasma meant that you had free electrons. And those free electrons were coupled to photons via Thomson scattering, which is a very efficient scattering process with a relatively high cross-section. And that meant that photons were tightly coupled to electrons. Electrons were coupled to protons via electromagnetic interactions, and that meant that photons were tightly coupled baryons. In other words, the mean free path of photons was extremely short. Photons could only travel a very short amount of time before being rescattered by Thomson scattering. And that meant that the universe was opaque. The universe, before recombination, was an opaque plasma, and therefore we cannot see anything before recombination. The universe was opaque. So recombination is the epoch when the temperature dropped enough for hydrogen to become neutral and stay neutral for the first time. That's to say, we have a process like this where we have electrons and protons recombining, giving you hydrogen and photons. Now, you might be tempted to use a simple back-of-the-envelope calculation to estimate the energy scale at which the combination happened. And of course, energy scale is given by the binding energy of the hydrogen atom. So the binding energy being the difference between the mass of the electrons and the proton and the mass of the hydrogen atom. And that's, of course, a Rydberg, the ionization energy of hydrogen, which is 13.7 electron volts. So you may think, okay, if the temperature of the photon bath and the energy is much larger than 1 Rydberg, than the binding energy, then of course hydrogen is going to be ionized and in thermal equilibrium with radiation. And that would be right. You might think that the energy scale for recombination should be 13.7 electron volt, which is the ionization energy, but that would be a little bit wrong by one order of magnitude, in fact. And the physics of it is very simple. The fact is that even when the temperature of the photon bath drops because of the expansion of the universe to 1 Rydberg, remember the photons are in an open distribution, and therefore there is a high energy tail of photons. And because there are many photons per baryon in the universe, there are about 10 to the 9 photons in your universe for each baryon. When a relatively small fraction of those photons having the energy higher than the mean energy of the Boltzmann distribution, it still means that those photons can very efficiently reionize hydrogen because they have sufficient energy to do so, and there's a sufficient number of them. So the physics of the thing is that you have to wait for those photons to cool enough so that you essentially have no high energy photons left, no photons in the high energy tail of the Boltzmann distribution that can reionize hydrogen. And that happens much later in time. That happens when the energy has dropped by another order of magnitude. So that's the short version of the story. In a qualitative way, you can look at the equilibrium ionization fraction, which we call XE, the number of free protons divided by the number of baryons, by the number of protons divided by the number of protons plus the number of hydrogen atoms. And you can use thermodynamical equilibrium considerations to derive an equation which is called the Saha equation, which looks at this, where you have on the left-hand side a function of the ionization fraction. So Xe equal 1 means that the universe is fully ionized, and Xe equal 0 means that the universe is fully recombined. And that function here is a function of temperature. So you can see here in the exponent, you got the binding energy divided by the temperature of the photon bath, as you would expect. There's another factor of KT here in front, but most importantly, there is this parameter eta here in front. And this eta here is the ratio of baryons to photons. Is the number that I was telling you before about. And this number here is of order 10 to the minus 8 times the baryon density. And this is a very small number. And the baryon density is 0.02, so this is even less than 10 to the minus 8. It's of order 10 to the minus 9. And because this number is very small, it means that you need for KT to drop much, much lower than B in order for the exponent in this equation to take over and XC to become 1. And so because of the high ratio of number of photons to baryons, because of the smallness of eta in the universe, the energy scale of recombination is not 1 Rydberg, we would expect, which corresponds to 10 to the 5 Kelvin, but it's about 0.1 electron volt, which is 2 orders of magnitude below that. And that corresponds to 3000 Kelvin. So what's recombination of the universe happens at a redshift of about 1000 or 1100. That's because the temperature of the universe scales as 1 plus Z. The temperature of the CMB today is 2.7, and so to get to a temperature of 3000, you have to have Z of order 1100. That's the temperature of the recombination energy. So there are two important things then, that it happens at 1100, recombination happens at 1100, and recombination is effectively almost instantaneous. In other words, if we plot the ionization fraction as a function of redshift, it's initially 1, and then it drops to almost 0. There's actually a leftover ionization fraction of order of 10 to the minus 4, and this drop here, which happens at 1100 by the energy considerations I just gave, it's extremely fast. The width of that is about 60 times of redshift. And so that means that all of the CMB essentially is created at the same time. And therefore, because the process is extremely quick, there is no time for the fluctuations in energy density in the CMB to be washed out. Or whatever the energy distribution, the energy anisotropies of the CMB were coming from the universe, at the time, they get frozen out almost instantaneously in terms of cosmological scales. And that is why we get a sharp picture, a sharp view of the last scattering surface through the CMB. If this delta Z was much bigger, if the recombination was a much more gradual process, we would get a much more fuzzy, much more smudged out picture of the CMB, which would not be nearly as useful in terms of determining the cosmological parameters. So we call this moment where the CMB is released, where the universe becomes neutral, electrons get captured by protons, and photons are now free to propagate because Thomson scattering is no longer effective. We call this moment recombination. We call it the last scattering surface, which is the surface here in the diagram I showed before, the surface at Z equal 1100, from which all of the photons from the CMB come to us almost freely. In reality, what happens is that those photons will propagate freely through the transparent universe until recombination reionization happens. When the reionization of the universe happens, you will get that the universe is reionized. In other words, it goes from being neutral to being ionized again when the energy emitted by stars is enough to ionize the interstellar medium. So what happens here at a redshift of about 10 or so, the universe gets reionized again by energy emitted by stars, and a fraction of the photons of the CMB is rescattered at redshift of 10. So this is the process of reionization. Reionization of the universe. It happens at the redshift of 10, and about 10 or 15% of the photons are reionized in that process. But most of the photons that we see in CMB have come from the last scattering surface without having been reflected since. Okay, so that's the origin of the background CMB, of the temperature, of the background photons. But of course, the photons are not exactly uniformly distributed. There are perturbations on top, and this is the most important and most relevant bit that we need to understand before we can make some statistical analysis of the cosmological background perturbation maps. Questions from you guys? Okay, so now the next thing I want to do is to talk about perturbations to understand qualitatively how and why we get perturbations on the maps, like the W map, sky map that I showed, and I want to sketch a statistical analysis and how we can understand it from a statistical point of view. Before I do that, I think now it's actually a good time to take a break, and so we can resume fresh and bright at 11:30. Is that okay? Okay. Let's all get coffee, and let's do it in about half an hour.